Now we've come to what really is the high point of the class. The fundamental theorem of calculus does two things. First, it clearly establishes a relationship between derivatives and integrals. And second, it uses that relationship to give us a very efficient way of evaluating definite integrals, a way that we'll be able to use to evaluate these integrals for any function where we can find an antiderivative. In other words, we're no longer going to be limited to finding the area under curves only for functions that we can interpret in terms of existing geometric area formulas. All right, so this is the first part of the fundamental theorem. It establishes a relationship between the definite integral and derivatives. Now, as we've done, so many times before, we're going to start with a function f that is continuous on a closed interval, right? Once again, we're really focusing on these so-called well-behaved functions, right? And what I'm going to do is I'm going to define this new function, capital F or cap f, right, to be the definite integral from a to x, right? So the first thing I want to be clear about is that this is a function, not a number or a constant. Assuming f is positive, you can think of this as being a function that describes the area from the starting point a out to an arbitrary point x. So if the original function was continuous on the closed interval, then our new function is also continuous on that interval, and it's differentiable on the corresponding open interval. Okay, now the equation here, this is the part that makes the connection I talked about on the last slide. If we take the derivative, notice the little apostrophe here, right? If we take the derivative of cap f, that is the derivative of that definite integral, then we get the original function back. Right? Now, think about what this is saying. If we take a function and integrate it, then differentiate the result, we end up back with the original function. Or if you think back to your college algebra classes, what we're doing here when we apply two functions in a row like this, integration and then differentiation, this is taking the composition of those two functions. And when the compositions of two functions cancel each other out and leave you back with your original input, those functions are called inverses of each other. So what we're really saying here is that the derivative and the integral are inverse functions. All right, so the second part of the fundamental theorem gives us a very simple way to evaluate. So this second part of the fundamental theorem gives us a very simple way to evaluate a definite integral, much simpler than calculating Riemann sums and much more broadly applicable than using formulas for the areas of shapes. So what this is, right, if we have a function, again, that's well behaved, right, is continuous on a closed interval, and where we can find an antiderivative for it, right? Then the definite integral from a to b is just the difference of the antiderivative evaluated at the two endpoints. Okay, now this isn't perfect. Finding antiderivatives can be much more challenging than finding derivatives. And in fact, there are lots of functions that don't have the kind of closed form formula like antiderivatives that we can write in that kind of neat way. However, as you'll see in the next lectures, there are enough functions for which we can find antiderivatives that this theorem is useful enough to rate being called the Fundamental Theorem of Calculus. Okay, so in the next lecture, I'm going to derive these two theorems. Right? I'm going to go through the proofs. So if you aren't following along with the theoretical side of the class, that's fine. You can skip over those, right, and go to the next one where we'll start looking at examples.